Okay, so let's get started. So by the way, have you all watched the week 12 lecture videos, or you are still watching it? So if you have watched the lecture videos, you just give a thumbs up. Okay, so only one watched the entire week 12 lectures. Okay, so yeah, in week 12 it is kind of last week, and more or less it's not heavy in concepts. But there are two key concepts, were covered in week 12. So one is loss functions, and another one is neural networks, right? Even though neural network was not covered in detail, but the skeleton of the neural network and what it does was discussed in the lectures, right? So the important thing is that we should understand different loss functions and why we go for these formulations. And again, in this session, we will solve problems at the end of the session, and then before that I will just show you the key differences and important insights that I observe when we use different sort of loss functions. Okay, so the central idea of going for or formulating different loss function, even when you come to deep learning, right, we always want we always use gradient descent based optimization algorithm. Most of the time you build the network and ultimately you use a gradient based optimization algorithm like backcrop. Okay, so in that sense, the idea is most of the problems, okay, many different sort of problems can be solved in the sense can be minimized or maximized using gradient descent and ascent, and they are especially these gradient based approaches are scalable, okay, meaning that if you have thousands of samples it works, if you have billions of samples again it works. Okay, so it doesn't matter how many samples you use, it doesn't matter the complexity of the model. Okay, so once you formulate a proper loss function, okay, you get an output from the model no matter how deep or how big your model is. Once you have a output of the predictions, then you have a proper loss functions, which can be used using gradient descent or ascent, then you can go ahead with it. Okay, so it is a single optimization algorithm or a technique, iterative algorithm, which is it has been standing the test of the time for past 200 years. Okay, so that is the idea. How do I use gradient based optimization algorithm? And of course, the requirement is that the function, the loss function that it needs to be differentiable. Okay, then only we can compute the gradients. So we have to ensure that, and therefore it has to be continuous. Okay, so all these things. And typically, of course, when we think about the classification problem, we are always interested in just counting the errors. Okay, it's a discrete count, 1 or 0. If there are 10 errors, there are no errors. Okay, so that is what we want to do that. But one problem with this that it is not differentiable, so we can't use gradient descent or ascent any methods. And of course, it's not convex, and moreover it is NP hard. Okay, so what does that mean? So even if you could take a set of boolean functions as inputs, okay, instead of continuous real valued inputs, even if you take n boolean inputs, then if you want to find the solution, okay, with all the possible outputs, then it is exponential. Okay, so it simply explodes. You can't enumerate on all these possible solutions, so the search space is quite enormous. Okay, so that's why it is NP hard. So we need some suboptimal solutions or some sort of approximate solutions using some surrogate loss functions. Okay, so that somehow gives us an idea about actual this 0 1 loss. Okay, so this is the setup. Okay, so we want to use gradient descent or gradient based algorithms, and these are all the requirements, and we go for different formulation of the loss function. Okay, so I want to use SVM, sort of SVM, then perceptron or whatever logistic regression. So for that, I have to formulate a proper loss function. Okay. So yeah, so the obvious choice is we can go with square error loss. Okay, so that it was discussed in detail. So we are going to stick with this notation. So we have a data set D with samples X and also the labels. The labels are encoded as +1 and -1. Okay, for various reasons. Okay, you may correlate it with SVM as well. Okay, and then we have this simple regression line W transpose X, and if you want the predictions 1 or -1, then we have to threshold it. Okay, so we use the sine function usually, or we can choose any different threshold for the sine function. Okay, but because it makes the function discontinuous, then we go with function as is. Okay, we are going to use this value of g as is, and then because it is continuous, then we can use a simple square error loss. Okay, so we just plug in the value and compute the error. Okay, and yeah, this formulation is straightforward. I'm just repeating this, and so if you need explanation, you just ask me. If I'll ultimately we end up with this expression. Okay, so g is W transpose X. Okay, it is going to be a scalar, any value from -infinite to +infinite. And then we have 1. Okay, and then we just square it. Okay, that's very good. So in general, this W transpose X can take in principle a value between anywhere between -infinity and +infinity, right? But for the time being, for the sake of understanding some multiple connections and concepts, let's limit it to -1 to +1. Anyhow, we are interested in the sign when we make a prediction. Okay, so the obvious question is, when do I get zero loss? For what value of this all these terms? So the answer is very trivial. So if I have this term equal to 1, then my loss is exactly 0. Okay, so what is the meaning that this term is equal to 1? So that we just look in detail. Yeah.
All the predictions are right.
Yeah. So one is that the condition 1 is my label is 1. Okay, the true label is 1, and W transpose X is also 1. Okay, so remember, now I am restricting the value between -1 to +1, and therefore it is allowed to take 1. So in this case, it is going to be 1. On the other hand, my W transpose X is -1, the other extreme, and the label is also -1, then the product is going to be 1. So my loss will be 0. Of course, the value can vary between -1 to +1, but we are just talking about the ideal condition. Okay, so really what happens in this interval, how the loss changes within this interval if my W transpose X value changes between -1 to +1. Okay, so can loss be greater than 1? Okay, so we can ask these questions, and for that we divide this interval into two halves. Okay, so where one we consider an interval 0 to 1, meaning that my W transpose X value is greater than 0 and less than 1. The other interval is -1 to 0. My W transpose X value ranges from -1 to 0. So we can plug in these values, and let's try to understand what this loss is actually doing. Okay, the loss function. So for the right half, let's say I'm considering the interval. I mean, W transpose X value result in 0 to 1. So I just take the extreme values, not any value between 0 to 1. Okay, and then let's say my true label is 1. Therefore, the product is also going to be in the interval 0 to 1. Okay, then if you plug in these extreme values here, okay, so let's say my prediction, I'm W transpose X is 0, then you will get the loss value as 1. If my W transpose X is 1, then you will get loss value as 0. So your loss will be within the interval 0 to 1. Okay, so which means here your loss value is going to be within the interval 0 to 1. Okay, so note that even my prediction is correct, my loss value is 0 only if W transpose X is exactly 1. So if it is less than 1, still there will be some loss value. Okay, so this is very important because loss 0.5 doesn't mean that my model is bad. Okay, and loss 0 is ideal case. Okay, and on the other extreme, right, if my label is negative label, the negative class, then you change the range. Okay, then my loss value is going to be 4 and 1. Okay, you just plug in, you can say it is going to be 4 and 1. Okay, which means this is fine because it is penalizing the misclassification. Okay, then we can simply plot this and see how the graph looks like. Okay, we can take the other interval as well. Okay, the other is the exact opposite case. Okay, so my prediction W transpose X value is going to be in the interval -1 to 0, but my true label is, again it's a misclassification, so the loss value will be in the interval 4 to 1. Okay, but if my true label is negative class -1, then it's a correct classification, so the loss value will be the 0 to 1. Okay, so this, if my classification is correct, okay, which means if my true label is 1, the prediction is also 1. My true label is -1, the prediction is in the negative. Okay, so then it is classifying correctly. Despite this, we have the loss values that could vary from 0 to 1. Okay, so that's what exactly this curve okay actually tells. Okay, still you incur a loss. Okay, 0 is what I want, but even for the right prediction, I can go from anywhere between 0 to this 1 value. Okay, but the question is, what happens if I go beyond the interval 1 and 1 and -1? Okay, so here we are just constraining the value to 1 and -1. Okay, but it is possible that this simple linear W transpose X can take any value beyond 1, right? So in that case, you can see that even if my prediction is correct, right? So okay, you can see that even if my prediction is correct, it is imposing a loss value, right? So I get W transpose X value as 2 and my true label is 1, then GY is going to be, what is the value of GY? So it is going to be 2, right? And my W transpose X can be 3 and my true label is Y is equal to 1. Then again G into Y gives me the value of, what is that? 3 minus 1, 2, so 2 square, which is 4. Okay, so the loss value increases even if my model is doing good. Okay, which means it is highly confident about its prediction, but the loss function is doing the exact opposite. Even for higher confidence score, it is giving a lot of penalty. Okay, that is one observation. Just keep that in mind. So we can see that square error loss function is not a good one in case of classification problem, even if it is binary classification problem. Okay. So if you have any doubts up to this point, you can ask. Then I just switch to this SVM Hinge loss. Then I try to compare these two. How the penalty is. The slide link. So you want. I haven't shared this slide link, by the way. So if you want it right now, if you want to watch the slide contents along with me, then you can use that link. But later I will share this slide link for offline viewing. Okay. So now we see the
other than binary classifications, for linear it is good, okay, sir. Squared loss.
Sorry, for which?
No, it is not good for binary classification. Other than binary, I'm asking like linear.
No, it is not good for classification problems at all. You can use this for regression problem. That is
Regression.
fine.
Okay. Okay, sir.
Yeah, but if it is about classification and going with square loss is not at all recommended.
Okay, and you
Then
have told
now,
something about if we increase towards left, we will incur some loss.
yeah,
Can you
that is true.
answer that part alone?
Moving, yeah. So let's say, for example, this case, okay, my G can take value, let's say -3.
Yes.
Okay, so W transpose X equal to -3, but my true label is 1. So the product will result in -3, right?
Yeah.
So -3 minus 1 is 4 square, right?
Yes, sir.
Yes, sorry, -3, yeah, 4 square 6. It should be 16. So in this case, it makes sense, right? Because my classification is, it is misclassifying the thing. So my the loss value is 16, which means it is penalizing
More.
the deviation very much, right?
Yes, sir.
For misclassification, this is fine, but if the loss value increases even for the correct classification, okay, then that is not fine. That is what the previous case is. So let's take this example. My G value can vary from 0, even -infinity to +infinity. Let's say my G value is now +4,
Okay,
meaning
sir.
that W transpose X is +4. My true label is 1. So the
1, 4,
product is
4,
4, and 4 minus 1, 3, 3 square,
3.
9,
Okay.
right? 4 minus 1, so 3
Yeah, yeah.
square, it's
Just
9.
9. Yeah.
So for misclassification, it penalizes heavily, but even for the right classification with high confidence, right? So
Okay.
what is the increasing value of W transpose X sales? It is highly confident about the prediction. That's how we go with, that's the one of the interpretations, right?
Okay, sir. Thank you, sir.
Yeah. Okay, so now, yeah, we already straightly used square laws. So the other thing is that we can go with a different laws such that it doesn't penalize the correct classification, but it penalizes the misclassification or wrong classification. Okay, so we want such laws, so we can view from that aspect, and also we can view it from the SVM perspective as well, right? So we are anyhow using W transpose X, and then we impose this margin constraints. So from the SVM perspective, you can think it of as, this loss is exactly doing what SVM is doing. Other perspective, we want the loss function such that it doesn't penalize the high confidence score, but penalize the misclassifications. Okay, so these are all two aspects. Of course, now we can use all these things, how we got into this loss definition. I'm not going into that, but conceptually what it does, can you see? So I'm just repeating the same table from the previous slide used for the square laws. So here you can see at the same setting. Okay, so I haven't changed anything. The setting remains same. So I'm just repeating the values. Okay, so here it is 1, 0. Can you tell me what will be the value here?
1.
Okay, why is that 1?
1.
Because
No, the
maximum.
interval. I want the interval. See how I'm just telling you how we got this 1 and 0, because my product GY can take value between 0 and 1. So I plug in these values. So I got the interval 0 to 1, right? So same thing I am putting it here. So what will be my interval?
0 to
My
1.
product can take value between, you just take the extreme values, right? GY, the lowest value is 0, the highest possible value is 1. So if you plug in this one, then what will be the value? So the
0 to
product
1.
of GY,
0, sir.
0
it
to,
is same, right?
yeah.
Okay, so there is no change here. So it is going to be the same interval. For the other hand, for misclassification, you can see it is penalizing heavily. Okay, but whereas it is not penalizing heavily. Okay, it is almost, this is quadratic, but it is linear. Okay, in terms of penalizing the misclassification. Similarly, I can do for the other half, okay, other range. So I can repeat the same. So same thing for correct classification is fine, but for misclassification is penalizing heavily, but this loss function is right, it is not penalizing that much. Okay, that makes sense why it is not penalizing that much. That's fine. But if that is the case, then why should I use hinge loss, right? So let's look at that aspect as well. Okay, so now as I told you, in fact, this W transpose X can take any value from minus infinity to plus infinity. Okay, so now recall that in a classification setting, let's say maybe this is SVM or it could be anything or just perceptron, and I have some margins like this, and I have a point here, okay, and I have weight vector something like this. So my W transpose X will be greater than 1. It is based on how far the point is, my W transpose X value can keep increasing, right? It can be 8, it can be 10, based on if it is very far away from the decision boundary, then W transpose X value will be high, okay? So it is possible that values can increase, okay? And this is good if it happens for the correct label, okay? So let's say my W transpose X value is, is varying between 2 to 10, okay, 2 and 10, that is really good, okay, and my loss and GY product will not change, the range will not change, it will remain 2 to 10. Then I plug in this into this squared loss function, and then it gives me a range between 2 minus 1, that is 1 square, and 10 minus 1, that is 9 square, okay. But what about this max one? What will be the range for this max now? We have this max of 0 comma 1 minus W transpose X dot Y, which is G. So what will be the interval for this? This interval is going to be 1 comma 81. Okay, which means my loss value will be varying from 1 to 81 based on my W transpose X. But what will be the output from this hinge loss for this interval?
Zero.
0 to 9. Sir.
Okay, 0 to 9 or just 0?
Zero, sir.
Yeah, okay, 0. So any other different answer? Okay.
Sir, if
Now
we
that
take
is going to be,
this,
yeah, please go.
no, sir, why I said 0 to 9 is if we take the upper bound of the value as GY as 10, then 10 minus 1 is 9. So maximum of 0, comma 9 will be 9 now, sir. That's why I told 0 to 9.
You look at carefully, right? So when you plug in the maximum value 10 here, what happens to the subtraction?
It will become -9.
Minus 9, okay.
So when
Okay,
you
sir.
take max, right? Okay, so
0.
what is the
Okay.
inference, right? Okay, guys, I already have this. Okay, what is the inference then? Is it good or bad? Do you think outputting 0 is good at this
Good.
for this setup?
Yes, sir.
Good, sir.
But what about the square loss?
That is
It is
bad for
giving higher loss.
higher values. Yes.
Okay, so we ideally want, right, for just give me a second.
Why we have taken max as 0?
I will be back in a minute. Yeah, sorry about it. Yeah, so that is a good thing. So someone was asking some doubt. I think Janvi.
Yeah, I was asking that why we have taken max as 0 here.
That's how, I mean, in fact, we are taking in this from the SVM definition, right? So it is like my ideal case is I want something like this. Okay, so ideally when we plot the decision boundary, right? This is the decision boundary and I have this vector here perpendicular to it, and any point on this vector, if we take a dot product between any data point that is exactly lining on this decision boundary, it will result in 0. So I use this 0 in order to make whether the data point belongs to positive class or a negative class. So this is like a baseline for me, right? Decision boundary. So that's why I have to plug in 0. So then only I can compare whether if W transpose X is greater than 0, this is positive class. If it is less than 0, this is negative class. So in this way, you can interpret why we are plugging 0. But by default, when you deal with soft margin SVM classifier, it naturally comes from there, right? By keeping the constraints, everything intact,
But
then we can.
there was written like max between 0 and 1 minus GY. So why we haven't taken any interval here rather than 0?
Why should you take an interval? Interval in the sense what?
Like if there will be max 0 or minus 9, so that's why we have taken here like 0 is maximum out of those. I'm asking. Are you
Okay,
there?
I'm not able to get the question.
Like
So one thing is you can see this as a constraint in SVM, right? So I put a constraint. So if you want from SVM perspective, then you can think of this as the margin constraint, right?
Epsilon, sir. The
Yeah, we
brain.
have this epsilon, all these things greater
got
than
it.
equal to 0,
I got it.
and all these things. Okay, so typically we have this. Okay, I'm just for completeness, I'm writing this. Okay, then equal to 1, and then we plug in epsilon here, and then we just rearrange all these things, right? So from SPM perspective, it naturally comes out of it, okay, keeping these margins in mind. But from the loss perspective also, we can justify this. Okay, so anyhow, now this loss function is doing good, which means for a prediction with high score, okay, which means high confidence, then you don't need to actually penalize, okay? So you don't want to actually update the parameters, right? So you want the gradient to be 0. So you want to ensure that the loss is 0 for even the marginal prediction or a prediction with high confidence. Whereas if there is a misclassification and based on the confidence of the misclassification, I have to penalize it. So I have to increase the loss function. Okay. So that's what this max function actually doing. Okay. So if you plot this max function for misclassification, you can the square loss is penalizing more. Okay. Whereas this max is penalizing linearly. Okay. Because it's a linear function, and then it is penalizing linearly. Okay, so if you plot these two, you will see. So one is the squared loss,
Sir.
and one is Hinge loss. Yeah.
So we can take this max of 0, comma 1 minus GY as epsilon, sir.
1 minus G. So
Max
it will
of
be
that.
something. Yeah, yeah. So the epsilon I or general epsilon is equal to max of this term. So that's how. So if you remember correctly, that's how it is actually coming in from the soft margin. I mean, it exactly aligns with this soft margin penalty, right? So you can cross check it by looking at these penalization. Okay, so you draw this SVM classifier, okay, with some margin, and you allow this data point to be here and also to be here, okay, and also allow some misclassification in the wrong side, and then compute the loss, and then you can see it exactly penalized based on this margin. Okay, so for right prediction, it is not penalizing. Okay, so for all the bad data points that is falling above this margin gamma, the loss is 0. Okay, let's say these are all positive class and they are all above this margin gamma. So naturally it is, g dot y has to be greater than 1, okay, for this to be above this margin, which means our max value will be 0. Okay, so we are not penalizing. But if my positive class comes below this margin but above the decision boundary, we are still penalizing it, right? So if this data point is below the margin, what will be the dot product of this data point with the weight vector? Will it be greater than 1 or
Less than 1.
so it will be less than 1, right? So if it is less than 1, then we still have the gradient. The loss is not 0. We have based on, say for example, if it is 0.5, my loss value will be 0.5. Then I have to update the parameter, okay, so that it changes the decision boundary. So this is what soft margin does, so SVM classifier does. That's what we naturally want the gradient based optimizer to do the same. I hope it makes sense now. Or you give some thought to it after the session, maybe you get that. Okay. Okay, so these are all the points. Okay, so if your prediction is correct, even with very high confidence score, okay, which means far away from the margin, then there won't be any gradient update, in the sense loss value is equal to 0. So that is good. But whereas square loss doesn't do that, it penalizes heavily, okay, even for right prediction. And again, for wrong prediction, which means if my point is falling in the either below the decision boundary or within the margin, okay, so there are two ways. So when we say it is a wrong prediction with respect to this loss, I have a boundary here and I also have the margin here. So there will be a non-zero loss value if my true value falls here, or it will be heavily penalized if my data point comes here. Okay, so in both the cases we will have non-zero loss value. Okay, so it is similar to what the SVM does. Okay, of course, still you can correlate it with the regularization, right? So in fact you can do a lot. Okay, you compare this is a regularization term, so you can ask questions like what happens if the weight value decreases, what happens to the margin if I penalize the weight, will the margin increase or decrease? Okay, all these things you can play around, but the important concept is this. Okay, you should understand how it correlates with the SVM, and also you should understand why it is better than squared error loss. Okay, so that is the thing I wanted to convey in this particular session. Okay, so I hope that's clear. Now, keeping this aspect in mind, we can go with, we can go and compare the other loss functions as well. Okay, so we can take once again the logistic class. Okay, naturally you can extend, and the derivation is quite straightforward. So you take this loss definition, okay, and you just plot this loss, and you can clearly observe that the loss value is not going to be 0 at any cost. Okay, unless my W transpose X is infinity, in the sense the probability assigned to the right data point is near 1 or 0. Okay, so exact 1 and exact 0, that typically won't happen. But this is somehow a smoothed version of this hinge loss. Okay, so again it penalizes more or less near to the hinge loss, but less than the squared loss. Okay, for misclassification. Okay, so you can study all these things, but from the gradient perspective, this function is really smooth, so we can compute the gradient, and also it is monotonous. By driving this to a proper value, proper W transpose XY, and then ultimately it behaves as if we are implementing this logistic regression using maximum likelihood estimation. Okay, so the idea remains same. So you can plot this and also compare, but I would really like you to understand the squared laws and the Hinge laws thoroughly. Okay, and this perceptron, okay, that I need to discuss. And logistic, you can impose few more constraint, or you take a constraint from this SVM and then it becomes a perceptron. Typically, that is how we see perceptron and SVM, right? We remove all these margin concepts and we let the perceptron to find just the decision boundary that separates the data points. So if you remove that constraint, then you will have the perceptron loss. And then again for logistic loss, you have this smooth version. Okay, but practically you still encounter near zero value if your model is really good. But in principle, you can say it never reaches zero. Okay. Yeah, perceptron the same thing. So we are just removing that margin. Okay. It is exactly aligned with this SVM concepts as well. You just remove the margin and you will have this. Okay. And of course, in the lectures I think also explained and how do we relate this to the stochastic gradient descent algorithm, but that's fine. Okay, so now I hope you understand how all these four losses are connected. Okay, and now when you go with real world problems, oftentimes you want to misclass. If there is a misclassification, you want to penalize this very heavily. Okay, so from the penalty perspective, you have to choose out of some 10 plus loss functions. Okay, so you have to study the loss function carefully and then keep these aspects in mind. If you are using gradient descent, then the loss function has to be continuous. And if you are also thinking about penalizing the misclassification heavily, and then you have to think about how all these loss function penalizes the misclassification. Okay, so these are all the core concepts. Of course, there are few more loss functions are there, but I'm not touching on it. Next, we will go to neural networks, but if you have any doubts, you can go ahead and ask. Yeah, please go
Hello,
ahead.
sir. Yeah, I have doubt from lecture slides on perceptron loss, hinge loss, modified hinge loss. Sir used word batch size. I'm not getting that.
Sorry. Can you repeat that in the perceptron?
Using perceptron hinge loss, modified hinge loss, right? Sir
Mm-hmm.
used word batch size and unit learning rate. I'm not getting that.
Okay. Okay, let me take a look first. So this is week 2. I hope I have met this teenager slides. Okay, week 12 here. Let me switch the tab. Okay, here it is. I hope here it is. What is that last function? This one. Yeah. This one, right?
Yeah, just below.
Okay.
Yeah.
This one.
Yeah.
Okay, so this is a gradient descent based weight update rule. In gradient descent, we always have this learning rate. Then you set the learning rate to 1. This is equal to perceptron. So I'm not sure what is the perceptron rule used in this MLT course. Of course, there are multiple ways of using the perceptron rule. So is this the perceptron rule used in this course? See, okay, let me tell you the concepts, but I'm not sure how it was defined in the MLT course. But in perceptron, if there is, you take a data point and the perceptron classify it correctly for the given weight, then you won't make any weight update, right?
Yeah.
But if it misclassifies, then you will add or subtract the data point, right?
Yeah.
So that's what this function also does, right? You have yt, which is a label, and then you have xt. So this is fixed 1 or minus 1. So based on the error, either it is going to add the weight or it is going to get subtracted with the weight, right? Based on the true label, right? You will end up adding or subtracting. So the rules remains same, right? So that's what my take on it.
But when true level not match, then we have to update. Otherwise, not update.
Yeah. See here, when do you get the gradient value to 0 here? According to the perceptron loss function, if my classification is correct, the gradient will be 0 because of, I'm not sure, I'm not able to write on it, but if my classification is correct, the loss value is 0, which is a flat region. If my classification is, if there is a misclassification, then my loss value will be taking on this linear part of the loss, right?
Yeah.
So if the model correctly classifies, then the loss is 0. So if the loss is 0, then the gradient becomes 0. There won't be any update, right? So it exactly aligns with how perceptron actually updates the weights.
Okay. Got it.
Okay. Okay, I'm just stopping this. Yeah, so if you have any doubts so far, you can ask it. Otherwise, I just switch to neural networks class. Okay, so now I'm using the presentation prepared by Karthik from the previous, I think, maybe in this few terms ago. So I thought this presentation is well known, so I'm just using it. Okay, I hope you all have access to this presentation, right? I mean, I'm just getting it from the drive folder, so you should also be. Okay. Okay, so let me go over this quickly. And before moving on, so if you have any specific doubts that you want an additional clarification, with respect to this neural networks, you just let me know so that I can stop at that point and explain. Okay. Okay. So neural networks, as you know, so far all the classification models that we learned